Swayam Prabha. Digital India. Educated India.
Hello and welcome back to another lecture on control systems. So over the last few lectures we've been discussing Nyquist criteria, and in today's lecture we've promised that we'll compare this tool of root locus, which was a time domain tool, with the two frequency domain tools that we've learned, that is Bode plots and Nyquist sketches, right. So we already started to look at this in the sense that we took a toy example of a system with 3 poles and no finite zeros, right, and we drew the 3 different kinds of course the root locus is the same, but we drew 3 different locations of the closed loop pole. So today let's start by looking at what the corresponding Bode plots for those particular values of gain k look like. So recall that in the previous lecture we have drawn this root locus of the system GC given by k upon s plus a into s plus b into s plus c, where of course a, b and c are all positive real numbers. So in the first case we choose some low value of gain k. So let us try to quickly sketch what the Bode plot is going to look like. So we know that initially it has a low frequency asymptote that's flat, then it goes at minus 20 dB per decade, then it probably increases to minus 40 dB per decade, and finally it goes to minus 60 dB per decade, right. So let me sketch that. So if I smoothen it out, this Bode plot is probably going to, this magnitude plot is probably going to come down like this. It is going to continuously come down, unlike the phase plot it does not tail off, yeah, it is going to continuously come down like this. So this is going to be the Bode plot, and the phase plot of course is going to go from 0 to minus 270 degrees in steps, right. So it is going to settle at some value like this. So this is 0 and this is possibly minus 270 degrees, right. So now from this Bode plot we know that, let us say we have a 0 dB line here. So this is our 0 dB line here. So this is basically where the 0 dB line cuts this magnitude plot is the gain crossover frequency, and at that gain crossover frequency we want to find out what the phase is and how much phase budget we have. So if this is our 180 degree line, let us say this is minus 180 degrees, so this is the amount of phase margin we have at that point, yeah. But of course the phase crossover happens here, so this is basically the GCF, this is the PCF, the phase crossover frequency, and at the phase crossover frequency we find out what the magnitude is, yeah. So that means this is the amount of gain margin we have. In other words, we can lift this Bode plot up by exactly this much amount without losing stability, right. So this is of course the plot of the open loop transfer function GC, and we have seen that if we increase the gain k up to that much, that is the amount of margin that we have. From the root locus this would mean that you have this value of k is equal to k1 here, and this is the k crit here, kc, right. So what is the ratio of kc to k1? That means by how much can you raise k1, by what factor till you get to kc. So if k1 is 2 and kc is 6, then you can raise it by a factor of 3. So this gain margin is exactly going to tell you that. Of course in this plot it is going to tell you gain margin in decibels, yeah. So that is it, that is basically it. So you first have the gain crossover frequency, then you have the phase crossover frequency, yeah, that is typical of a stable open loop system which is also expected to be stable in closed loop, okay. So that is why you often see people say this, that gain crossover frequency is less than phase crossover frequency is a good thing. Yeah, the implicit assumption, as I also said when discussing Bode plots, is that the open loop system is stable. Yeah, all our discussions are now predicated on the assumption that the open loop system is stable. Alright, what about this situation here? You see, now whatever amount of margin I had, I have now raised this value of k. So this phase plot does not change, the phase plot still remains the same because I have not touched the phase, I am just changing this k, I am playing around with this value of k. What I am doing is I am basically raising this gain plot, yeah, so that wherever I earlier had this phase crossover, yeah, now this gain crossover was earlier occurring somewhere over here, now this gain crossover is shifting to the right. By lifting this plot, yeah, now it is exactly at this phase crossover frequency that I have this 0 dB crossing as well, yeah. So this is my gain crossover as well as my phase crossover frequency. This is the critical point, and at this critical juncture I have this pair of purely imaginary poles on the brink of crossing over to the right half of the complex plane. Okay, so this is the critical value of k. What if I exceed this? I do not want to, of course, because the system will blow up, but what if I did so? Then, well, bad luck, your gain crossover has now moved to the right of your phase crossover. So this is where your new gain crossover frequency will be. Of course, the phase plot remains unaffected as before. So this is where your minus 180 degree crossing happened, yeah, this is where the minus 180 degree crossing happened, yeah. So you better reduce the gain is what this is telling me. So the gain margin is negative, yeah, so you have to reduce the gain now, you have to reduce the gain. So if you are already at k2, then by what factor do you have to reduce the gain k2 to come back to the left half plane, yeah, that is what this negative value of this gain margin is telling me. So this is negative gain margin. Also you see at the gain crossover frequency you have already crossed over, yeah, so your phase margin is also negative. So it so happens that in case of a stable system, either both your gain margin and phase margin are positive and the system is closed loop stable, yeah. So if you have an open loop stable system, either both your gain margin and phase margin are positive, in which case if you put that open loop system with that particular choice of gain in a closed loop configuration, the closed loop system will be stable, or both your phase margin and gain margin will be negative, in which case you have to bring down the gain in order to stabilize it. But if you kept that value of gain, then both your gain margin and phase margin will be negative and your system, which was open loop stable, will now become unstable in the closed loop. Now all this is very well and good, this is all we understand based on Bode and root locus and fairly transparent. Does Nyquist also convey this sort of information? So you might ask, what is this interpretation of phase margin and gain margin for a Nyquist plot? So before we sketch these 3 Nyquist plots here, I will come back to this slide. Let us quickly try and understand typically what happens in case of a stable system. So did I draw this? I do not exactly recall, but anyway. So these are your 3 poles. Let me draw the Nyquist the contour here. Of course I do not need the dent now because I do not have the, so I have just this, I have just this D contour. So this is A, this is B and this is C. So let me quickly draw this Nyquist. By now we should be fairly comfortable with this. So what happens at A? What happens at the point A? Well, I know that at the point A the phase contribution of all of these fellows is 0, yeah, and I know that it starts from somewhere over here, which is basically given by K upon ABC, yeah, that is basically the real part of GC, this is the imaginary part of GC, right. So this is how I start off. Now what happens as I keep going up towards B? You see all of these angles, they keep increasing, yeah, at any test point here they all contribute this phi 1, phi 2 and phi 3. So as I keep going up in this direction, yeah, it will be phi 1 plus phi 2 plus phi 3, but of course with a negative sign because these are all poles after all, right. So they will be in the denominator. if you see the phase of the overall transfer function GC, that will be some negative angle. What does that negative angle mean? It means that I have to go along this fourth quadrant until at the point B, what is the phase? All of them will have 90 degrees, so they will contribute minus 270 degrees. So minus 270 degrees means what? Minus 270 degrees means a rotation in the clockwise sense of 270 degrees, yeah. So basically I will have a Nyquist plot that comes somewhere over here, yeah. And then from B to C, what is the picture? Of course, it is inconsequential in so far as our stability deduction is concerned, but you can clearly see here immediately that there will be this crossing of this negative real axis, yeah, which is something that should interest us, because now we want to find out if this negative real axis crossing is happening to the left or to the right of the critical point, that is minus 1 comma 0, yeah, in this plane, in this GC plane, right. Anyway, so we know how to evaluate that. We have to basically equate the imaginary part of the open loop transfer function. So we basically say that solve for imaginary part of GC is equal to 0, yeah, and based on that then you find out which is a feasible solution, the real solutions in terms of omega, solve for omega in imaginary GC is equal to 0, yeah, and then you get your answer there, right. Anyway, but again for the sake of completeness, from B to C, you see at B it is minus 270 degrees, at C it is plus 270 degrees I believe. So the net change in going from B to C, so this is A prime, this is B prime, and of course this is somewhere here is C prime. So in going from B to C, the net phase change is 270 minus 270, that is 540 degrees, right. So a 540 degrees change means a counterclockwise rotation of a full circle and then a half circle, yeah. So a full circle rotation like this and then a half circle, yeah. Of course this is very minuscule, right, it will hardly matter, you will hardly be able to see this, yeah, you will hardly be able to see this. So again I think I have already drawn this figure, but nonetheless, so from here if you try to draw this, let us see, yeah, okay, that did not turn out so well, yeah, that would be it, right. So that would be the figure, right. And then from here of course I now no longer need to re-sketch this, I can just draw the mirror image, yeah, like this. So now you see, as before this is telling me the same picture. If within this blue segment I have minus 1 comma 0, then I am in trouble, because then n is equal to minus 2, p is equal to 0 and z is equal to 2. So that means I have two of those closed loop poles in the right half plane. On the other hand, if I have this here, if I have the minus 1 comma 0 point somewhere over here to the left of this crossover point, which of course can be evaluated by solving for this, yeah, then I am safe, because then n is equal to 0, p is equal to 0, which gives me that z is also equal to 0. So therefore there are no closed loop poles on the right half plane and I am safe, the system is closed loop stable, right. That is all I wanted to start with, right. So therefore it is important for me to understand where this is, right. So obviously from this figure what does it tell you? It tells you that if you choose very low values of k, then this crossover point is going more and more to the right as you keep decreasing k, but as you keep increasing k, this crossover point moves to the left. So therefore this tells us the same thing, right, that increasing k is bad, decreasing k is good, yeah. So with this in mind, I wonder what would be the phase margin or gain margin. So suppose you start with small values of k initially, right, you have initially k is equal to 0 at open loop, then you give very small values of k. So obviously at that point this minus 1 comma 0 point will be outside, right. So you find out what this crossover is and find out this distance, yeah. So you find out what this magnitude is at this point, right, and then 1 by that magnitude of g j omega, and this frequency is called the phase crossover frequency. In the Nyquist plot you can also see why it is called a phase crossover, because the imaginary part is 0 at that frequency. What does it mean to have an imaginary part 0 and the real part negative? It means that a phase of minus 180 degrees or plus 180 degrees, yeah, that is consistent with our understanding of Bode plot. The only thing that might be a little inconsistent is that here we are not considering the logarithmic scale. So here we are not considering the gain margin in decibels, instead we are saying it is this 1 by this, right. So that means I can keep increasing, I can afford to increase my gain k by a scaling factor of something given by the gain margin, right, and I will still not include this minus 1 comma 0 point inside the Nyquist sketch, yeah, inside the Nyquist plot, and therefore I will be closed loop stable, right. So that is how this Nyquist interprets the gain margin. What about the phase margin? So what is so special about the phase margin? Phase margin is evaluated wherever the gain crossover happens. What do you mean by the gain crossover happening? Gain crossover means wherever this g of j omega is equal to unity in magnitude. Now if you have a complex number on the Argand plane, yeah, if this is your z, then obviously this length of this line is the magnitude, yeah, this is the magnitude. So if you want to draw all possible complex numbers, so this is a fixed complex number, let us say z is equal to 1 plus 2j, yeah. So if you want to draw the locus of all possible complex numbers which have the same magnitude as this number z, then you better find out what the magnitude of z is. What is the magnitude of z? It is 2 squared plus 1 squared is equal to square root of 5. So what are all possible complex numbers on the Argand plane that have the same magnitude? Well, of course, it is something we are very familiar with, it is a circle of radius root 5, right. So any complex number that lies on the periphery of this circle with radius root 5 will have exactly the same magnitude as this chosen z here, right. So here if we want to find out, after all this is also a complex plane only, right, it is just that the real axis instead of being just the Argand plane is the real part of GC and is the imaginary part of GC. So if we want to find out, yeah, where this magnitude of this transfer function GC, this open loop transfer function GC equals unity, I better draw a unit circle. So I better draw a unit circle like this, right. So let me draw that unit circle here. So suppose this is the point unity, so it must pass through this, so maybe something like this, yeah, or maybe if you have chosen a different gain k, then this Nyquist plot would look something like this, and of course okay something like this, and something like this, yeah, and let us say this is where your minus 1 comma 0 point is. So let me draw a unit circle. Of course it does not look like a circle, it probably looks more like an oblong shaped object, but yeah, this is the unit circle. I am claiming that this is the unit circle, okay. So look, there might be multiple points, of course this is the unit circle. So of course there might be multiple points where this unit circle cuts this Nyquist plot in general, but here let us say this Nyquist plot cuts this unit circle over here, yeah. So now you see what is the notion of phase margin now in view of this revelation, yeah. You see, if by some means I were to rotate this Nyquist plot, so I am not talking about changing the magnitude of this, okay, a pure rotation of this. So if I am going to just stretch around this Nyquist plot and rotate this, so what is the phase at this point, yeah, this is still some, this is called the phase margin, and why I will explain in a moment. So let us say this is theta, the angle between this intersection point with the unit circle and this negative real axis is called theta, and this is my phase margin is what I am claiming. What is the interpretation of this phase margin? It means that if I rotate this Nyquist plot by a further angle theta, then this point where this intersection had happened, this critical point, yeah, where this intersection with the unit circle had happened, this would have come into this imaginary, into this real axis here, and would have given me this equality of phase margin and gain margin. So that is the amount of phase budget I have, that is the phase margin, okay. So from this Nyquist diagram, by just looking at this unit circle intersection and the intersection with the negative real axis, I can actually figure out what my gain margin and phase margin are. Again, caveat, we are only talking about open loop stable systems, okay, where it makes sense to talk about positive gain margin and phase margin as something desirable, okay. So that is the interpretation. So now, having seen this interpretation of phase margin and gain margin, let us try to go back to this figure. I have already drawn the general look, how this will look, right. So the Nyquist in one shot is going to tell me, yeah, what this phase margin gain margin is and whether it is stable or not, yeah. So let us see. So here it is because it is stable, you will come across a situation where this -1, 0 point is not encircled. So here you will see that like this, yeah, something like this, right. So you will see that this point is excluded. So you draw any test radius like this or test phasor like this, and it does not cut this at all. Even if it were to cut, yeah, you can see that it will cut actually once in one direction and the second time in another direction, alright. So it really matters not, alright. So if you for example, if you drew this test radius through this point over here, once you will see it cuts in this direction and once it cuts in the opposite direction. From the perspective of this is counterclockwise and this is clockwise. So the net encirclement is 0. You can try out several scenarios and you will find that no matter what test radius you choose or test phasor you choose, it is always going to give you 0 encirclements. So that is consistent with what we understand. What about this situation? Now this is a bit tricky, you do not know whether to include this or exclude this as stable, but that is always the case with marginal stable systems, right. So here you will see that this is going to kind of intersect at exactly the point, yeah, so this is going to be it, yeah, right. So this is going to be it, yeah. So this point is going to be exactly -1, 0, the critical point, yeah, the Nyquist diagram will pass through this critical point, okay. So that means that at that point you exactly have the roots on the brink of migrating from the LHP to the RHP, okay. And finally, if you increase k even further beyond this critical k, if you choose very high k, then you will have this Nyquist diagram that will look something like this. Of course, the shape will, as I say, the shape will remain the same, yeah, this is very close to the 0 point, yeah, sorry, just a minute, yeah. So of course the shape will remain identical, but the encirclements will change, and now you see that this is what happens. So you have this point -1, 0 somewhere over here, and you draw any test radius, yeah, for example, you draw, let us say, this test radius, and you see there are two clockwise encirclements, which means n is equal to -2. So of course n is equal to -2, p is equal to 0 means z is equal to 2. So already two of your poles have already migrated, which is exactly what the root locus also tells us, right. So you see that side by side, if you are given a Bode plot, a Nyquist diagram and a root locus, you should be able to relate one with the other and see how things turn out, okay. So this, of course, this one has negative gain margin, yeah, this one the gain needs to be reduced in order to stabilize this, it has got too high a gain now, yeah, this one has got 0 gain margin. So gain margin and 0 gain margin and 0 phase margin. So this one has 0 GM, 0 PM. This one has positive GM, positive PM, and this one has negative GM and negative PM. So I want you to be able to appreciate this even by looking just at the Nyquist diagram, yeah, not just from the Bode plot, alright. This gain margin and phase margin, these are notions associated with the frequency domain. So now that you have learned about this Nyquist diagram, here also you will see that if you draw this, if you look at this real axis crossing here, it is at a point beyond -1. So yeah, so this 1 by this, yeah, is going to be less than 1, no, because this point is greater than unity. So 1 over this, which is the gain margin, is less than unity. Yeah, if you take the logarithm of that, then it is going to spit out a negative quantity. Log of a fraction is negative, right. So therefore you will have negative gain margin as suggested by this Bode plot as well in the decibels. Yeah, so that is what negative gain margin means, we are talking about in decibels. Similarly about phase margin, yeah, you need to evaluate at the gain crossover frequency. So you draw this unit circle here, yeah, and you see that whichever one is closest, yeah, you draw this unit circle passing through this, yeah, and you see that you do not have any margin for error here, yeah. This is already, yeah, this unit circle, if you draw this unit circle through this point here like this, yeah, and you try to find out its crossing, yeah, at that crossing if you take the angle, for example this plot, remember this is the segment that we drew earlier, right. So this segment obviously had multiple crossings, but the one crossing that matters has already ended up here. So if you have to have a phase margin, you better reduce this phase, no, you have to bring it down. So you have basically a negative phase margin here, right. Yeah, you cannot add any more phase lag, yeah, you have to add a phase lead, you have to bring it down. So you have to rotate it in the counterclockwise direction, which is tantamount to adding more lead, okay. So that is consistent with our understanding of phase margin. Phase margin is the ability to withstand phase lag. So if your system cannot withstand more phase lag, it means it has very little phase margin. What are the things that are responsible for adding phase lag? Well, for one, you know that a pole adds a phase lag, right. But I would say that the picture of all of this we have drawn and the way we understood will remain incomplete unless we discuss one crucial aspect. So let me take this final case, okay. So since we have just talked about this varying this gain k here now, which will effectively change the gain k, right. So it is basically changing the magnitude plot, but now there is also a way to change the phase plot alone without affecting the magnitude plot, and we have already seen one way of doing that, that is adding a delay term, yeah. But apart from a delay term, there is also another way of doing it. What if you added, for example, something that stands for as a proxy for a delay, the Bode approximation. So what if you added a term like this, you see the magnitude of this is equal to unity for all omega. We have seen this in the Bode plot, right, because the corner frequency is at t by 2 by t, and at 2 by t you have both the corner frequencies, the pole and the 0, so effectively it is like a flat line, yeah. So what if instead of having this gain k, we were to add this term, a term such as this, okay. So let's try and understand this in the light of our new revelations. So we have again root locus, Bode plot, and Nyquist diagram, okay. So as before we chose the same system, k upon s plus a into s plus b into s plus c, and in addition we have a term such as this, which is probably a delay that has been approximated using Bode approximation, first order Bode approximation, to look like this, okay, right. So now let us look at what the root locus, let us think of what the root locus is going to be. For one, if you want to cast it in a root locus format, you have to write st by 2 minus 1. But if you want to maintain it in this form, then you better draw the complementary root locus, right? We have to draw the complementary root locus. So what we do is, for root locus sketch, as we have already seen for non-minimum phase systems, we first convert it to st by 2 minus 1 upon st by 2 plus 1 times k upon s plus a into s plus b into s plus c, and then we look at the complementary root locus, yeah, because now that we have already made this negative, so we make k negative. So we look at the root locus as k varies from minus infinity to 0, that will make sense, right. So if we want to vary this k over positive range of values, then in this case, once we have already swapped the sign of this non-minimum phase term, this non-minimum phase 0, we better look at the complementary root locus, yeah, okay. So since we are, it will also give us a bit of good practice and refresh our memory. So let us see, we have these 3 poles here, and we have this additional pole due to this additional time delay like term, and a symmetrically placed 0 like so. So now we know that in a complementary root locus the rules change, and therefore you will have the root locus existing here, you will have the root locus existing here, and you will have the root locus existing here, right. So that is one thing for starters. Also eventually at some point this has to cross over here, right, yeah. So how does this crossing over happens? How does this crossing over happen, right? So you will see that the direction of the asymptotes will also change for the complementary root locus. So unlike earlier when it was 60 degree and 300 degrees, right, 60, 300 and 180, here it is going to be 0 degrees, 120 degrees and 240 degrees. So you will see that in this case the root locus will look something like this. So this is one asymptote, these are the other 2 asymptotes, and something will happen like this where this branch will migrate like this, yeah. So by sketching the complementary root locus we see what is happening here, yeah. Now what about the Bode plot? A Bode plot we do not really care about swapping signs and all, because this is perfectly cast in the form of the Bode plot actually. In fact all we need to do is we need to pull out this k by abc, and we have s by a plus 1, s by b plus 1, s by c plus 1, yeah, but that is okay, we will not get into those details, you already understand that. So for the Bode plot, what does this mean? You see the magnitude plot is not going to change at all, it is going to remain exactly as it is, because this fellow, when I add here, this fellow does not contribute anything to the magnitude, it contributes a pure phase of minus 180 degrees. Remember non-minimum phase zeros teaming up with the poles, yeah, the action on the phase plot of a non-minimum phase 0 is the same as the action of a pole on the LHP, right. So if that is the case, then this will actually contribute to an additional phase of minus 180 degree as omega tends to infinity, yeah. So earlier, let me draw the earlier phase as well. So let us say this is my earlier phase which was going at minus 270 degrees, now this phase will be brought down a further 180 degree and it will go up to let us say 270 plus another 180, 450 degrees, right. So you see now the phase plot will be brought down further. What effect does this have? Well, the gain crossover frequency does not change, yeah, because the gain plot is unaffected. So this is still the 0 dB line and this is my gain crossover frequency, but at the gain crossover frequency earlier I had a phase like this, yeah, but now this is my minus 180 degree, now I have a phase of this. So if earlier in the absence of this time delay like term, this Bode approximation of time delay, this is the amount of phase margin I had, but now I have only this much phase margin, yeah, that's only to be expected. Moreover, now you see that my phase crossover frequency, yeah. That phase crossover frequency is also earlier, maybe it was, maybe it will not settle down like this, but here it will cross over something like this, yeah. So maybe earlier my phase crossover was happening somewhere here, but now my phase crossover happens over here. So although one of the things does not change, the gain crossover frequency does not change, but remember, at the gain crossover frequency the value of phase changes, therefore the phase margin changes. What else changes? Of course the phase crossover frequency will change. The phase crossover frequency, because of this additional phase lag due to the time delay like term, the phase crossover frequency now moves to the left, yeah. And if the phase crossover frequency moves to the left, well, automatically the gain margin will change, yeah, because now earlier if the phase crossover was happening here, I probably had a gain margin like so, but now I have a phase crossover happening here. So because the phase crossover frequency has changed, now my gain margin is this. So effectively what I am seeing here is that this additional time delay like term, the Spade approximation of the time delay, is detrimental both to the gain margin and to the phase margin. But all this is well known, yeah. You might wonder, well, this is understandable from the Bode plot, we already seen this, so why are we wasting time on this again? Well, the interesting bit is, when we look at this Nyquist diagram, how does it manifest itself, yeah. So you can take this as an exercise, it is not very difficult. All that you have to do is you have to remember that this st by 2 has to be, the sign has to be changed, because for a Nyquist plot also we tend to write in the s minus z form, right. So you have to write it in the s minus 2 by t form, right, and then sketch the Nyquist diagram with a negative sign outside. If you do that, yeah, if you do that, then you see at s is equal to 0, this is again going to be k by ABC, so it is going to start somewhere over here like this. But now earlier if you notice this Nyquist diagram, it was coming up to here, right, at plus 270, but now it will suffer from an additional rotation of another 180 degrees. So now the Nyquist plot will come all the way like this and end up here, yeah. So this addition of the phase causes this Nyquist plot to rotate, okay, and this is exactly why phase margin is significant, yeah, because now this Nyquist plot has rotated by some additional 180 degrees. So this term had the additional effect of doing nothing but, you know, twisting this Nyquist plot somehow around this, around its corner, right, around this point where it is intersecting with this origin, where it is converging to the origin. Instead of converging along the positive imaginary axis, now it is going to converge along the negative imaginary axis, so an additional phase, okay. And this most certainly in the Nyquist plot also is going to show that, well, if you do not have sufficient phase margin and sufficient gain margin to start with, yeah, you might very well have already encircled now, yeah. So remember, maybe the original Nyquist diagram probably looked something like this, yeah, but now if you rotate this, that means whatever was 180 degrees away somewhere here, this fellow has now come here, yeah. So now you have twisted this and you have gotten this fellow to come here, yeah. So that is the net effect of this pure rotation. Of course a time delay term, a pure time delay term e to the minus st will also be a pure rotation, but we are not going to draw the Nyquist diagram for that. We have only dealt with Nyquist plots for rational functions, so we will leave it at that, right. So I hope that with this you understand that in some sense this phase margin and gain margin is, as I already said earlier, a measure of robustness. That is, how much perturbation, how much time delay, how much changes in gain can the system tolerate before it loses closed loop stability, right. And Nyquist is also telling you that in a very transparent way, the distance from the critical point. So I must warn you at this juncture that, well, you know, sometimes people often think that just looking at the gain margin suffices. If you have a positive gain margin, how bad can things get after all? But you know, consider some scenario like this, yeah, where you have something like this, okay, or maybe let me make it even more nasty. You have something like this, right. So let us say this is your point -1, 0, right. Now if you are looking only at the gain margin, yeah, you look at the phase crossover frequency. So this is going to be the phase crossover frequency, right, and you might think that you have this much gain margin to play around with, right, and you might be reasonably happy. But unbeknownst to you, because of some rogue-like behavior of the system, maybe some flexible structure or who knows what, right, it totally depends on the kind of system that you have, the model of the system, the mathematical model, right. In reality, your proximity to this point -1, 0 is much smaller. So even if you haven't really given it sufficient gain to have this point, crossover point, sufficiently close to -1, 0, and you might think you are safe, yeah, but in reality maybe you increase the gain a little more, yeah, and this thing then starts to affect, right, then it starts to sort of encircle, right, and then you are in trouble, right. So it is actually risky and tricky business to look at just one of those metrics like gain margin. You should look at both the gain margin and phase margin, whereas look here, if you just looked at the gain margin, it was almost impossible to predict that such a thing could have happened. But if you were astute enough, and if you had looked at both the gain and the phase margin, right, then you would actually also draw this unit circle here around this. You would draw this unit circle here and you would immediately see, hang on, this point is perilously close to -1. Why? Because I have a very little phase margin. So although the gain margin may be very good, yeah, the phase margin is very small, okay. So therefore be very careful, do not just look at one of those metrics and infer about stability or otherwise, or stability margin or otherwise, look at both of them. For a good closed loop stable behavior, you would ideally want good gain margin as well as good phase margin, okay. If you just have one of them to be a reasonably decent positive value and the other is pretty bad, well then you should be alert, okay, because there can be these nasty sort of things that might be going on, okay. So before we close with our discussions on Nyquist, and with which we shall actually end our discourse into classical control, because the next few lectures and the next topics that we shall discuss will be what is termed as modern control theory, okay. We will look at state space approach, state variables and things like that, and we will motivate why those state space approaches are important, okay. So this is actually going to be our last topic insofar as classical control is concerned. So before we close with this, let me just give you another thought to carry forward with this, right. So far whatever we have done here is about the open loop transfer function, but sometimes people might be interested in the closed loop behavior, right, because after all at the end of the day we put this transfer function in a closed loop and then we study the transient behavior, and then we want to find out what things like settling time, bandwidth, rise time, etc., overshoot, resonant peak and things like that, etc., evaluate to, right. So we wonder, can Nyquist help us in that regard? Well, let us try and see. So suppose you have Gc upon 1 plus Gc is equal to your G closed loop transfer function, right. Now suppose excuse me, suppose you want this closed loop transfer function's gain to be m, yeah, suppose you want this to be m, right. So then m is equal to, and you fix up, so this is a number, a fixed number. So suppose I want the closed loop gain to be this m, okay. Then I wonder at what frequency should I be operating, right. So this is going to be nothing but Gc mod of Gc upon 1 plus Gc. So let R equal to real part of Gc, of course this is all evaluated at j omega, and let I is equal to imaginary part of Gc, of course at j omega, right. Then what can we write? We can write that our fixed number m, yeah, the number that we desire to be the closed loop gain is nothing but R plus I or rather r squared plus I squared under root upon r plus 1 squared plus I squared under root. Okay. So let us get rid of this radicals and stuff, and so we write m squared is equal to r squared plus I squared upon r plus 1 squared plus I squared, and we push it to the other side. So we have m squared r squared plus 2r plus 1 plus I squared is equal to I squared plus r squared. So if we take common, then m squared minus 1 times r squared plus I squared, yeah, and then we have plus m squared 2m squared r plus m squared is equal to 0. So let us divide throughout by assume m is not equal to 1. What if m is equal to 1? Well, if m is equal to 1, yeah, if m is equal to 1, if m is equal to 1, then we see that this r and I squared, these terms cancel, and what we are left with is 2r plus 1 is equal to 0, or r is equal to minus half, right. So basically the real part of the open loop transfer function is going to be minus half, yeah. So that is a vertical straight line in the, so if this is my GC plane, so this is the real part of GC, this is the imaginary part of GC, yeah. So this real part of GC is going to be minus half, so that is going to be a vertical line like this passing through the point minus half. Okay, so we discount it. So for the time being we will just let it be, we will just assume that m is not equal to 1, because we know what happens when m is equal to 1. So we have explored that. So let us say m is not equal to 1, then what can we write? We can write r squared plus I squared, and we can divide throughout by m squared minus 1 plus 2m squared upon m squared minus 1 times r plus m squared upon m squared minus 1 is equal to 0. So let us use the same trick of completing squares. So r squared plus 2 times m squared upon m squared minus 1 times r plus the square of this term. So that is basically m to the power 4 upon m squared minus 1 whole squared, yeah, plus m squared upon m squared minus 1 is equal to, now we have to counterbalance this term we have added, let us add it on both sides, right. So that means we have r plus m squared upon m squared minus 1, I hope I am not making a mistake, yeah, plus, okay, there is a plus I squared missing, I can already see that, yeah, so this is plus I squared is equal to this m to the power 4 upon m squared minus 1 whole squared minus m squared upon m squared minus 1. Let me go to the next slide. So we have r plus m squared upon m squared minus 1 whole squared plus I squared is equal to, if I take m squared by m squared minus 1 common, so then I will be left with 1 m squared by m squared minus 1 minus 1, so that is going to give me m squared minus m, so that is 1, so it is going to give me m squared by m squared minus 1 whole squared. But what is this the equation of? Yeah, this is after all the x axis, this is the y axis, so this is typically the equation of a circle. So this is circle with center at m squared by m squared minus 1 and radius equal to m by m squared minus 1, right. That is what this is. So therefore, if I want to draw the constant closed loop gain locus on the GC plane, here is what it would look like. So for m is equal to 1, it passes through this point minus half, so this is for m is equal to 1, alright. What about for m greater than 1? yeah. So for m greater than 1, yeah, this radius is going to be something positive, and this center is going to be also something positive, but even greater than the radius, right. So it will never really intersect the, so you see that the center is further away, so it is at minus, sorry, yeah, it is at minus m squared by m squared minus 1. So the center is further away from the origin than the radius, than the length of the radius. So therefore, let us see, what can I say about this, let us see, hang on. So if m squared is greater than, so if m is greater than 1, yeah, so this is the radius, this is the center, yeah. So the center will be somewhere here, of course the y axis of the center, so this is the real part of GC, this is the imaginary part of GC, alright. So yeah, and what about when m is less than 1, let us try and think about it a while. So when m is less than 1, you see m squared minus 1 is then negative quantity. So minus of m squared by m squared minus 1, that is the center, will be on the right half, yeah. So here is where your typical center would be, yeah. So for m, so when m is less than 1, then your center will be to the right of the imaginary axis. When m is greater than 1, then the center will be on the left, okay, and this is at minus half, at this point it passes through. So I am just wondering what happens at m is equal to 1, of course this is this, so they should not intersect, right, because of course they should be disjoint, the locus should be disjoint. So can we somehow see if, yeah, so you will see that these are going to be your different circles, sorry. So this is going to be your one of your circles, this is going to be another of your circles, yeah. So this is how the circles are going to be, but those circles are not going to really touch each other, yeah, those circles are not going to really touch each other. So as m increases to larger and larger values, yeah, so that is what happens, as m increases to larger and larger values, you see the radius actually decreases, yeah, the radius actually decreases. So that is the conclusion. So this, the larger the circle, the smaller is the value of m, of course this is for m greater than 1, and circles on this side will be for m less than 1, so this is for m less than 1, okay. The point is, why did I draw this on this GC plane? Now if you think about it a while, this is the origin, if you now want to sort of superpose this Nyquist diagram, yeah, if you now draw this Nyquist diagram on this same graph here, then from the Nyquist diagram you will exactly know, suppose this Nyquist diagram starts from here, yeah, then from this Nyquist diagram you will exactly know that at what value of omega what will be your closed loop gain, right. So that is an efficient way. So these are actually called the M circles, yeah. So far we have seen that this Nyquist can be used to tell about stability, conditional stability, phase margin, gain margin, things like that, but now it turns out if you have a plot, because these are not very difficult, these are system agnostic, in the sense that you can always draw this circle given a particular m, yeah, this circle is fixed up by its m. Once you tell me that what is this m, yeah, if m is 1.5, then it will always be the fixed circle. So suppose I have a graph paper on which I have already drawn a priori a lot of these circles for different values of m which interest me, yeah, and then on that graph paper I superpose excuse me, on that graph paper I superpose my Nyquist diagram, yeah, then the intersection of the Nyquist diagram with these circles will exactly tell me that at what value of frequency I will have, or what value of omega I will have exactly that closed loop gain, yeah. So that is how closed loop behavior can also be inferred from the Nyquist diagram, provided you have already a priori or beforehand drawn these M circles on the same graph. Hold on a sec, so there is this correction that needs to go. Yeah, the center cannot be just a single coordinate, it's, yeah. So this is the center, yeah, and radius is this. So I leave it to you to check that with this sort of a center and radius configuration, neither for m greater than 1 nor for m less than 1 can this ever intersect, or these circles can ever they touch or intersect this line at m is equal to this minus half, right, this line that has a constant real part of minus half. So for m greater than 1 it is always going to remain to the left of this, for m less than 1 it is always going to remain to the right of this place, okay. So I leave that to you to check as an exercise, okay. So by the same token there are also things called n circles, yeah. So what are these n circles? So now these were about the magnitude, so n circles are about the phase, okay. So I leave that to you as an exercise to derive what the equation of the n circle will be like, but I will just give you some leads into how to approach this, okay. So suppose you have this GC as before upon 1 plus GC, so again R is equal to real part of GC and I is equal to the imaginary part of GC. So this is your GCLTF. Now suppose you want to find out the phase, sorry not Q, the phase, the closed loop phase, yeah, because after all this M was basically the closed loop gain, yeah. By the same token you have this closed loop phase which is denoted, for want of a better letter in the English alphabet, by N. So this is called tan inverse GCL TF. But what is this? You see, what is this G? This is basically R plus JI upon 1 plus R plus JI. So tan inverse of this, I mean this is argument of this, sorry, I should not write tan inverse right away, I should first write argument, yeah. Now I am in a position to write tan inverse. What is the tan inverse? So this is basically tan inverse I by R, that is the phase of the numerator, minus tan inverse I by 1 plus R, yeah. So let me just lead you on to this and then you might simplify and see that it is indeed going to turn out to be the equation of a circle. So let us see how far we can push our luck, and let me see how far I can make error free calculations. So basically tan inverse A minus tan inverse B is going to be equal to tan inverse A minus B, so that is I by R minus I by 1 plus R, I by 1 plus R. So as I said, tan inverse A minus tan inverse B is tan inverse of A minus B upon 1 plus AB. So it is 1 plus I squared upon R into 1 plus R, yeah. So this is tan inverse, let us see, 1 plus R times I minus IR upon R into 1 plus R divided by R into 1 plus R plus I squared upon R into 1 plus R, yeah. So that is going to be equal to tan inverse, of course from the numerator IR cancels out, so you just have I here remaining. Of course the denominator has this term common, the numerator and the denominator parts have this term in common, so this will also cancel out, right. So therefore you have this I remaining on top, and below here you have R squared plus I squared plus R, I believe, right. So therefore since n is a fixed number, now you have tan n is equal to I upon R squared plus I squared plus R, yeah. I mean it really does not matter, you can call this tan n and call it n hat, yeah. So this tan of n you call it n hat, this entire thing you call it n hat, and then that you equate to I upon r square plus I square plus r, I believe that is correct so far. So, you have r square plus I square plus r is equal to I by n hat. Yeah. So, in this case you have to complete both squares, right. It is typically, you can already see, so complete this as an exercise and find out what the radius and the center of the n circle would be. Yeah, you will see that you will have to complete the square with r. So, obviously r, I can immediately see that it is going to be r minus half whole squared, yeah, r plus half whole squared if I am not mistaken, right. Yeah, r plus half whole squared, and of course with I you will have this 1 by n, so 1 by 2n I suppose, yeah, minus 1 by 2n hat whole squared will be equal to 1 by 4 n hat squared plus 1/4. So, I have managed to derive the so called n circle equation. Now, what is the point of all of this? The point is, just like in the Bode plot, the Nyquist gives us this frequency response for the open loop transfer function, yeah. But now with this m circle and n circle, you see what you can now do is, you can take this real part of GC and this imaginary part of GC, and you can draw these different m circles and n circles for different values of m and n, right. And now suppose you draw the Nyquist plot superposed on that, right, then what do you get? Yeah. So, what you get is something like this, you will have several of those m circles like this, yeah, you see these are m circles, of course they will not be touching, and you might take this as an exercise to check that as m increases the circle gets smaller and smaller, yeah, on this side of the line half, yeah, this is the vertical line passing through half, and then these are basically the m circles for m smaller than 1, yeah, here the bigger the circles are, the bigger are the values of m. So, this is for m less than 1 and this is for m greater than 1, as I drew in the previous case as well, right. And now similarly you have n circle. So, see n circle, you see the r, the center, the real axis coordinates, they are fixed, yeah. So, what does that tell you? It tells you that this will be some circle that will be centered at r is equal to half, which is basically on this vertical line, yeah. So, the center will be on this vertical line, depending on whatever n you choose, yeah, this circle will shift and also the radius will shift accordingly. So, as n increases the radius decreases, yeah. So, basically as your phi increases, the closed loop phase increases, the radius decreases. So, it becomes a smaller and smaller circle closer to the axis, right. So, you will get these m circles and n circles, right. Once you have drawn these m circles and n circles, then at any given frequency you see the intersection of this Nyquist plot with the m circle and n circle, and you know that the closed loop frequency response means that at that particular frequency of omega, yeah, wherever whichever m circle it encircles, it intersects with this Nyquist plot, that will be the value of the closed loop magnitude, and whichever n circle it intersects with at that particular value of omega, that is the closed loop phase of the system. So, using this, so notice that how easy it is now. This m circle and n circle can be drawn without any concern for what the system is. This is system agnostic, yeah. But with this itself, just by superposing the Nyquist sketch on this, you now get the closed loop frequency response very conveniently, yeah. So, you kill two birds in one shot, as it were, right. So, with that we now come to the end of our discussions on classical control theory. There are, of course, as with any other topic, several things that still remain which would lead us to delve much deeper, but unfortunately we do not have time for such in a one semester course. Plus, when there are additional topics such as state variables and several other interesting modern control topics which we really want to cover in this course, we really cannot afford to linger on this any longer, but hopefully with whatever you have learned about classical control, and whatever remains will not be beyond your grasp anymore, right. So with that hope we conclude this lecture. Thank you.